Hello, we're now going to talk about one of the most fundamental results in all of control theory, the Nyquist stability criterion. So what does this let us do? The Nyquist stability criterion lets us make predictions about stability of a closed loop system based only on properties of the open loop system, in particular properties of the open loop unstable poles and properties of the Nyquist plot. So what's the sort of general setup we're dealing with? Suppose we have some system or some process that we wish to control, and we have an input-output model for that system. This will typically be a transfer function model or a state space model, but we'll make a comment to this effect. Nyquist stability criterion actually doesn't require either of these types of models. You could just have some more model based on data or something like that instead. So we have some process that we wish to control using its inputs, and we want to control, or we can measure these outputs here. And we have a controller that we're interested in implementing, and we're about to close the loop, and we want to try and make some prediction about whether or not our feedback will be stabilizing or not. I mean, as we'll see, feedback design, you typically want to do a lot more than just stabilize a system. You're looking to improve performance and robustness properties and all sorts of things, but stability is like the most basic requirement. So we have some setup here. We have a controller that's picking the inputs to our process. We have some measurements, and we're about to close the loop, and we're using negative feedback. So we're right on the verge of closing things. We've not quite closed our loop, but we do have some idea what this thing called L of S is. L of S is the product of the transfer functions P of S and C of S. So L of S is called the return ratio. We have some idea of what this return ratio is, and we want to know when we close the loop whether or not we're going to end up with a stable or an unstable process. And this is what the Nyquist criterion allows us to deduce or make predictions about. And it tells us that the number of unstable poles of L of S, so the return ratio transfer function or the open loop transfer function, is equal to the number of unstable poles of 1 over 1 plus L of S. And I'm sure you're all familiar now that all of the closed loop transfer functions all have 1 plus L in the denominator. So these are the closed loop unstable poles. So the number of open loop unstable poles is equal to the number of closed loop unstable poles plus the number of anti-clockwise encirclements of -1 made by the Nyquist plot of L of S. And we'll get into what this means shortly, but the key thing for our purposes here is this is something that depends on the open loop return ratio, L of S. So what we have are two properties of the open loop system, whether or not it's stable in open loop, and if it's unstable, how many unstable poles does it have, and then something to do with the Nyquist plot, which is something that we can get from our transfer function model, or something that we could get experimentally. We could apply a bunch of test signals and build up the Nyquist plot that way. And that's what I mean by you don't necessarily need a transfer function model. And based on this, we can work out the number of unstable closed loop poles. And in particular, if we want the closed loop system to be stable, that is, we want this term here to be equal to 0, then we see that the number of unstable open loop poles must be equal to the number of anti-clockwise encirclements of the -1 point made by the Nyquist plot. And you've probably come across a slightly simplified version of the Nyquist stability criterion, which applies to open loop stable systems. So if the open loop system is stable, then this term is also 0. And we want 0 here, this is 0, and therefore we need there to be no encirclements of the -1 point made by the Nyquist plot. But here we have a more general version that applies in the unstable case, and will even tell you how many unstable poles you get should you be predicting instability. So this is the Nyquist stability criterion, and what we want to do in the rest of this mini lecture is just derive this using the argument principle that we built up in the past. And then we'll go on and do some examples after that. So if we wanted to derive the Nyquist stability criterion with the argument principle, well, what would we do? We would definitely be analyzing the complex function L of S. It's appearing in both of these objects here. We've been studying complex mappings for the last 2 mini lectures, so for sure it's going to involve this, and so we might as well draw on our 2 copies of the the complex plane. We have our input S plane, and then we have our output, I guess L plane in this case, but our output complex plane over here. Now, we've got various other things. We've got unstable poles, and we've also got this Nyquist plot. And so where do these things live? Well, unstable poles correspond to values of S that make certain transfer functions blow up. So unstable poles live in the S-plane. The Nyquist plot, however, lives in the output plane, and in particular, the Nyquist plot is the plot of L of S for values of S is equal to j omega. So we've got some pieces coming together. This is good news for the argument principle. The argument principle was connecting poles and zeros in the S-plane in some region to winding number type encirclement criteria in this output plane. So we've got a lot of the right pieces. So let's just keep going. The Nyquist plot next. So we said the Nyquist plot is the plot of L of S for values of S is equal to j omega. So S is equal to j omega, this just corresponds to the imaginary axis. So this is the curve S is equal to j omega. Even better news, we've started to get a curve. So we have this input curve and we get some output curve, and it might typically look something like this. So this is L of j omega when we input this curve here. So that's good. We've started to build up the pieces that we need to apply the argument principle, but we're missing some bits. So the argument principle needed closed contours. So having this curve here, this isn't really getting us very far. And also when we talk about unstable things, we're talking about poles in the right half plane. So we have a natural region in mind, but now we hit our first problem. We would love to pick the right half plane to be the region on which we apply the argument principle, but that's not allowed. If we remember, we said that the region had to be bounded, so we couldn't pick an infinite region. So we can't pick the whole right half plane as our region, but we can pick something arbitrarily big inside the right half plane. So, well, yeah, this seems to make sense. We don't want any poles, or we're interested in poles in this region here. So we could make this our region R. And now we could use the argument principle to say something about poles and zeros in this region R. Does that mean that we're already doomed? After all, this is a statement about stable or unstable, so surely we would have to cover the whole of the right half plane. Otherwise, there's no way this is going to work. Maybe we don't pick the region R big enough and there's some other unstable pole that's just really far out. And actually, this worry is, at least in theory, valid. So there are extra conditions that you have to apply to the function L of S in order to be able to predict stability on the basis of a region of finite size like this. And these are very much kind of academic concerns, I guess. I mean, when I said should you be worried about only being able to guarantee something about a region R of finite size, I mean, really, in practice, who cares? It's not going to make any difference here. I mean, you shouldn't just blindly trust equations no matter what. In practice, you never need to worry about these technical cases, but they're nevertheless kind of interesting to explore or to think about. So in what cases could you get away with a finite size of region R? Well, if somehow you could guarantee that you had no poles when S got very, very large, that would do it, because you could you could use your argument principle on some semicircular region, make it large enough, and then you're sure for values of S bigger than that number, you can't have any poles anyway, so you've covered yourself. And so what are some situations where that's enough? Well, it turns out that when L of S is a rational function, that's always the case. So if L of S is just the ratio of two polynomials based on the numbers that are in the coefficients of that polynomial, you can be sure that when S is sufficiently large, there'll be no poles. And so this kind of argument about stability based on a region of finite size, no problems. What's another case? If L of S tends to 0 for large values of S, then we see that 1 plus L of S, yeah, there can be no poles there. So we're not worried about that case either. And this is why you shouldn't be worried in practice, because any process in practice is going to behave like a low-pass filter when the frequencies get high enough. So for sure, L of S is going to be going to 0 as S gets very large, and this kind of finite region argument will work. However, interestingly, this is not enough even when we start to include delays. So technically speaking, you could build transfer functions using just delays and rational functions which corresponded to differential equations. Those are like two most common types of building block, and a finite region will not be enough. But this is kind of definitely a tangent. In practice, you don't need to worry about it, but maybe it's interesting to think about, and it's good to know that there's some extra limitations to the theory in here. And in fact, you can cause an incredible amount of mess just with rational functions and delays. You can even push things to the point where different definitions of stability will give different answers, which is something that's quite common in the study of nonlinear systems. Definitions of stability matter, but it's typically said for linear systems you don't need to worry about that kind of thing, but actually you do. But anyway, getting back to all of this, we're going to pick some finite region R, and we're going to assume whatever we say about this finite region R is going to be enough to conclude stability or not. So let's just get going. So we know that to apply our argument principle, we have to take a closed contour going around our region R, and ideally that contour should be in the anti-clockwise direction. And we already kind of see another irritating thing, is when producing our Nyquist plot, our contour went that way, resulting in an arrow going like that. And we don't want to change the direction of Nyquist plots. So we're just going to have to take care of that. But we'll get onto that in a second. The other thing we have to do is we have to turn this into a closed contour. So we have to close things off. And the way you would typically do this with your Nyquist plots is you have to reflect them in the real axis. So this was the Nyquist plot for positive frequency. This corresponded to going from here, and then frequency got larger and larger and larger, and it came around like this. If we start here and we go negative frequencies, it goes the other way. It looks something like that. What's going on here? Well, this is precisely this thing I was talking about of L of S going to 0. So this is one of those transfer functions where L of S goes to 0 when S gets very large. And this means that when we go along this part of the contour, our Nyquist plot, it is in there, it is going along that contour, but it's just arbitrarily small. If L of S wasn't going to 0, we would have to draw on some curve corresponding to moving around this part of the Nyquist plot. This part of the boundary of the region R. Anyway, we're making some progress. We've got a curve. It's going the wrong way, but fine. We've ended up with another curve in the output space. So we are, in principle, ready to apply the argument principle. And I'm going to modify things slightly. We've drawn the image of L of S, so we put in these inputs, this is the outputs we get. What would happen if we instead plotted 1 plus L of S? Well, that would just have the effect of shifting the whole Nyquist diagram to the right by a length of 1. And if we now think back, the argument principle was all about counting encirclements of the origin. If instead we look at 1 plus L of S, so the encirclements of the origin of 1 plus L of S correspond to the encirclements of the minus 1 point of L of S. So this is the Nyquist plot of L of S. This is the minus 1 point. If I count encirclements of minus 1, that's like counting encirclements of the origin of 1 plus L of S. So now let's apply the argument principle, but to 1 plus L of S with this shift of encirclement counting. And so what does the argument principle say? It says that the number of anti-clockwise encirclements and in this case of minus 1 by L of S is equal to the number of zeros of 1 plus L of S minus the number of poles of 1 plus L of S. And here is the number of zeros and poles in this region R. So number of zeros of L of S in the region R, and similarly in the region R. Okay, fine, but that was for contours going anti-clockwise. So if this contour was going that way, this statement would be true, and if we reverse the direction of this contour, we would reverse the direction of this contour. Okay, so the number of anti-clockwise encirclements of minus 1 by this L of S, and if we want to reverse the contour so that it's going the right way, we just have to put a minus sign in here. So putting a minus sign here will flip this back to being the direction that we actually drew. So this is what the argument principle tells us. Now, how can we relate it to what's going on up here? Well, what are the zeros of 1 plus L of S that are in R? So if 1 plus L of S is 0, then 1 over 1 plus L of S is a pole. So this quantity here, this is the number of unstable poles of 1 over 1 plus L of S. And similarly, how about the poles of 1 plus L of S? Well, the denominators of L of S and 1 plus L of S are the same. So if a number is a pole of L of S, it's also a pole of 1 plus L of S. So this is the number of unstable poles of L of S. And again, we just need to bear in mind that unstable here means no poles in this region are. So as long as we're satisfied with that, or we can prove that that's enough through some other method, then we're done. And you see, just by swapping these things over, we get exactly the statement of the Nyquist criterion that we had up here. So there we go. We have the Nyquist stability criterion and how to derive it using the argument principle. Let's now just do an example.